Well, should we get started? I think we have quorum. So good morning, everyone. Welcome to the ESNet Quantum Network technical talk for October. Our guest is Rob Knegjens with QuTech. And sorry, Rob, for brutalizing that. I tried to hit it. Who's working on a quantum network discrete event simulation tool called NetSquid. And look forward to learning more about that. Rob, thank you very much, and the floor is yours.
Thank you, Andrew, and for inviting me. Okay, so this is the outline of my talk. So I'll motivate why we decided to create NetSquid at QuTech several years ago, then how it works, several use case examples it's been applied to, and then wrap up very briefly how you'll get started using it and an outlook of where we're planning to go with it. Quantum communication allows us to network together quantum devices. And when we do that at long distances, the ultimate goal is to build a quantum internet, so an infrastructure for being able to send quantum information to between arbitrary locations in the world. But quantum networks are also interesting at short distances in the challenge of realizing scalable quantum computing. So under the assumption that most of the different quantum computing technologies being worked on today will reach some kind of physical limits or challenges that will limit their ability to grow. It's natural to network these processing cores together at short ranges, short distances, so to be able to entangle them and achieve modular quantum computing. So in that sense, quantum network applications, quantum networks provide a very diverse selection of applications. So the most classic would be quantum key distribution, secure communication, and similarly also in the realm of quantum cryptography, things like secure identification and secret sharing. But they can also, in the future, facilitate, as I said, modular quantum computing or distributed quantum computing also remotely, and remotely also delegated or blind quantum computing, where you can prepare quantum states locally and then send them to a quantum computer in a cloud and trust that actually that quantum computer will be blind to what you're trying to compute. Another promising application is atomic clock synchronization using entanglement set up with quantum networks. And on the quantum sensing side, to do interferometry, such as long baseline interferometry of telescopes. So these different applications rely on different levels of functionality from quantum networking, so some of these applications, like quantum key distribution, are already possible with technology that's commercially available today. What I call trusted repeater nodes already exist and can be, maybe a famous example is the one between Beijing and Shanghai. So here, quantum key distribution can be achieved by having these trusted repeaters that can read out and re-encode the keys and pass them that way. So moving up in the lab, entanglement has already been demonstrated using satellites and in labs, and that will of course allow for device-independent versions of quantum key distribution. And things get more interesting as you add capabilities like quantum memories. Then you can really go towards applications requiring forms of computation. So as I was just saying at the beginning of the talk, at QuTech, so where I work is the quantum internet. I work within the quantum internet division, and within that division, we have three main research directions. So one is focused on experimentally demonstrating sort of the cutting edge of quantum networking. One of the tasks I actually showed on the previous slide is trying to achieve an entanglement-based network using memories, and the hope is to be able to build a metropolitan version of that between, at the moment, 4 cities in the Netherlands. So the group of Hansen and also Tito are involved in that. Complementary to that is a group or the lab of Tim Timano are working on networkable quantum computing devices using defect centers in Diamond. So here to be able to use these defect centers not only as quantum computers, but also their optical interfaces to achieve a modular architecture for quantum computing. And then finally, the more theoretical focus is to not focus only on the hardware layer, the physical layer of the quantum internet, but also the control plane and the software needed on top of that, all the way up to studying interesting applications on quantum networks. So moving towards why we felt the need to develop a simulator for the quantum internet, we motivated a bit the challenges in realizing a quantum internet. So the quantum internet, especially as we see it, is an infrastructure for generating remote entanglement, which is then acts as a key resource to be consumed by different applications. The key building blocks here are quantum-enabled nodes, so different locations with quantum devices, memories, processors, linked by physical channels such as optical fibers or free space channels, links by satellite. And these physical channels then allow the nodes to also generate this entanglement. Here you see an example of two nodes using a Bell state measurement between them to do a form of heralded entanglement generation and to produce an entangled state. And that entangled state can then be used or consumed by an application, a classic example of which is quantum teleportation, where a qubit entangles with one of the entangled qubits in one node, then both are measured, and then by exchanging the classical corrections to the other node, you've teleported that quantum information from one node to the other. So the key resource being remote entanglement, it's been a natural task. What are the sort of important performance features of a quantum internet? And that is to achieve a high rate of this remote entanglement generation and with sufficient quality or fidelity. And in a real quantum network, those two metrics are hampered by loss and noise. So these physical channels are generally very lossy for the photons they're using to send quantum information, and the processes taking place in the devices are very noisy. Fortunately, there's methods to mitigate these effects. So the noise experienced when generating entanglement can be solved in different ways. And one way is a protocol called entanglement distillation. So if two nodes can generate one entangled pair between them of insufficient quality, in this example here, 75% fidelity, then they could repeat that process and generate two pairs that they hold in memory and apply a distillation protocol to probabilistically enhance that fidelity with some probability. On the other hand, the loss can be dealt with using what are called quantum repeaters. The loss is typically distance dependent. So in fiber, you have the attenuation scaling exponentially with distance. So by placing a repeater in the middle of this link, you're trying to generate entanglement between, you can then generate the entanglement on either side of this midpoint first. And when you succeed on both sides, you can do what's called an entanglement swap to end up with entanglement between the two nodes. So fortunately, these are in key protocols in realizing this quantum internet. The difficulty here is that they're stochastic in nature. So this distillation protocol can fail, in which case you have to repeat the process. The entanglement generation, depending on the technology you're using, can also be stochastic. And then if you consider the quantum repeater that's trying to produce entanglement on both of its arms before it can do the swap, one might, because of the stochasticity succeed much earlier than the other one, and its qubits then have to wait in memory, and they will decohere as they wait for the other one to succeed. And by the time you perform the swap, the fidelity you end up with may not be what you wanted. So you may also want to implement some form of cutoff. So these kind of challenges, and of course, creating chains of repeaters to be able to perform the swap in some nested or even parallel fashion to cover larger distances, ask for a very capable control plane above this physical layer. And so to realize a quantum internet is not just a question of developing very capable physical devices and answering questions about what are the better devices to store your qubits or to achieve distance with, but also what are the protocols you need to put on top of this layer to actually properly control your entanglement generation, your routing, and ultimately serve the applications you're trying to run. Now, taking all these things together is generally too complex to study with exact mathematical models, and therefore it's natural to turn to numerical simulation. And that was the motivation to work towards developing a quantum network simulator, so a numerical simulator, and the requirements we had for it were that it should be able to accurately capture these physical non-idealities and timing effects, because they're crucial for ultimately being able to determine the performance of your network, and being able to determine what the requirements of your quantum internet, given the applications you have in mind. Simulators should also be scalable to large networks, and versatile and ideally modular in how it approaches physical modeling. And with these ideas in mind, we ended up with NetSquid. So NetSquid is an acronym for the network simulator for quantum information using discrete events. So it's effectively a simulation platform meant for designing scalable quantum networks, as well as modular quantum computing architectures. And as I just mentioned, it aims to address these different simulation requirements, such as being able to accurately track time, scale to large quantum processing tasks, and be modular. And we aim for it to be util sort of across the entire quantum internet stack. So to be able to use it at the physical layer to explore requirements, use it to design and validate protocols and control software, and ultimately be able to answer questions about the feasibility of specific user applications. So NetSquid, yeah, we started 4 years ago with sort of a small team, really as a prototype, and over time it's pulled in people. We've also worked together with Sarah, which is the sort of academic HPC institute in the Netherlands. And we worked towards a public release last year. So we've been using NetSquid internally and also in European projects, but last year we made it publicly available with a free-to-use academic license. I can say a bit more about that later. And there's a paper we published this year that, well, I think contains a lot of what I'll present today in more detail. Okay, so that's the motivation for, and also NetSquid in a nutshell. I'll move on to describe how NetSquid works. Maybe if there's any questions so far, this would be a good moment. Okay. So NetSquid is a Python package. So yeah, you can install it from our pip servers, from our Python package index servers, using a tool called pip, sorry. And under the hood, it's written in C++ and Cython for performance. It is built out of these different sub-packages, which I'll explain in a bit more detail. But the main, I think, points are it has a simulation engine, which is actually a separate package that provides that does discrete event simulation. I'll also say a bit more about that in the next slide. And also at its foundation, it has a specialized quantum computing library. And on top of that are packages that take care of the modeling, both of the physical hardware and of the classical behavior, which we describe by objects called protocols. So at the base, as I mentioned, there's a discrete event simulation engine. So here, this was inspired by classical network simulators. So rather than stepping continuously through time in small steps, and NetSquid, the engine jumps between events, and entities in the simulation can dynamically generate those events as time goes by. And how that works in the quantum sense is that the qubits in the system are generally either traveling through channels or stored on nodes. And we don't evolve their quantum states until they're actually accessed by an event. So we do that retroactively. So a qubit sitting on a memory, the moment it's accessed by a specific entity, at that point, do we see how much time has passed? When was the last time it was accessed? Oh, it's experienced this much noise, or this kind of, yeah, maybe it's been lost. Here you see a cartoon example of how discrete event simulation would work in the case of quantum teleportation. The main points are that there's different entities, Alice, Charlie, and Bob. There's events that kick off this process. Charlie is waiting for start events. He generates qubits, puts them in channels, and then already pre-schedules events representing their arrival, assuming they're not lost. And then Alice, for instance, reacts to this qubit Charlie sent her arriving, and I say qubit, but I mean photon, or maybe some photon pulse, and will then access the qubit she had in memory. In this case, maybe yeah, apply noise depending on how long it was waiting in memory, and then perform some local operation on these two qubits she now holds locally. In this case, measure them using a Bell state measurement, and then pass on that classical information. And yeah, I can go on through this process, but those are the general ideas. This is just slightly more detail. So yeah, this core engine was based on actually, we developed this in-house as well, but actually based on a tool developed at TNO for design space exploration of networks. So we chose it because it's conceptually quite light and fast for what we need.
Hey Rob, how do you think about noise, the noise generation process? Is that a per channel defined characteristic, or is that an actual process?
I will describe a little bit more how we model the noise when I discuss this components module. But we apply noise models for different components. So it's part of our physical modeling of a network. So for instance, you define a channel and you may apply some depolarizing noise if it's relevant. And when the qubit comes out of the channel, at that event, it will experience that noise depending on how long it was traveling through the channel. And in the same sense, you have a quantum memory, you have a qubit on it. It's sitting there for some unspecified amount of time, but the moment you access it, we then evolve it to that point and applying the noise it would have experienced. Likewise, if you apply a gate to qubits in a processor, that gate may have a specific noise model, dephasing or decoherence or amplitude damping, and it's up to the user to specify their components. I'll come back to this, but that's part of the physical modeling step. From the quantum computation side, so NetSquid has its own library for doing quantum computation, and this differs from the quantum circuit simulator in that, well, we call it has a qubit-centric API. So what we try to encourage when programming NetSquid is to treat the quantum information locally. So you're holding qubits on a node locally. I mean, those are the only ones in principle you should care about. I mean, you can cheat and you have the freedom to also access qubits elsewhere. but we try and encourage these local operations. So as a user, you're dealing with qubits and you're not thinking about the states they might be sharing. And in that way, we can also be representation agnostic. So the actual state shared by these qubits could be represented in different ways, and the user doesn't have to think about that when they're dealing with these qubits. The states the qubits share, that's also handled dynamically. So it's not that for all the qubits that might ever exist in the network, we would sort of allocate a big register for them as you would in a quantum circuit simulator. But a qubit that's created may just have a state just describing itself, or when creating two entangled qubits, they may just be entangled, just share that entangled state between them. Well, here's an example of entanglement distillation. So there's two pairs of qubits sharing a state, but they don't, from a quantum mechanical perspective, know anything about each other until locally Alice and Bob apply this circuit to these states, and the result of which is they all become entangled. At this point, there's a larger state, but then as they're measured, the state shrinks again. So in this way, we try and sort of tailor the states to as big as they need to be at any time, which, as I'll explain in the next slide, is also more efficient in the quantum networking context. So I mentioned that it's possible that this qubit-centric API is agnostic of the representations. That choice is therefore also seamless. So we offer different quantum state representations that you can simulate with. And that's just a choice you can make once, and you can change, and it doesn't affect how you've written your simulation. So it's not when you're using one representation or another, you have to change all your code. So that's sort of hidden from you, because we encourage users to focus on qubits. And so that's just sort of a handy feature. But by having these different representations, the user also has a trade-off between what they want to simulate. So they can choose a representation that's universal in quantum computation, such as the Kett vector or density matrix formalism, or one that's more versatile with noise, such as the density matrix formalism. But these formalisms are quite inefficient in terms of storage. So they scale exponentially with the number of qubits we're trying to represent, and also computationally. The user can also choose for one of these other two representations, so the stabilizer states or graph states with local Cliffords. These are not universal representations, so they can't represent universal quantum computation because they miss certain gates. So they only support what are called Clifford gates, but they're much more efficient to store in memory. And certain quantum networking protocols only require Clifford gates in certain types of noise. So for instance, all the Pauli gates are included in the Clifford gates. And in the case, for instance, of stabilizer state, you can store the state very efficiently by not storing the state, but just the operators that stabilize it. And so in this sense, the memory only scales quadratically. And with this other formalism, it can even scale linearly if there's low connectivity, so a low degree of entanglement in the state. Yes, so by offering these different representations, it's possible to make a simulation that's more physically realistic as for a smaller network, or can scale to thousands of nodes by sort of giving up maybe some of your modeling freedom.
Could I ask a quick question?
Yes.
So when this is sort of like setting up a, like a SPICE deck or whatever for quantum simulation, and you've described qubits, but how do you describe the channel in your simulator?
Maybe the next slide will answer your question.
Okay.
Yeah.
Sounds good.
So these last two layers I described. So one is really the engine. So this there's nothing quantum about this. It's just a discrete event engine. And the qubits package is really just the quantum information. So it's saying nothing yet about the modeling. It's just how we deal with the quantum information. The modeling starts with these two sub-packages. And what we offer here are base components, so channels, quantum memories, detectors, that are composable of physical models. So you can start with a channel, and then you can add a specific loss model for it, for instance, describing the loss in fiber, or a specific fiber depolarization model to it, describing how a photon might depolarize inside it. Or and it's the same for the quantum memories or the detectors. So these are generic components, and they can be composed of each other as well. So here you see sort of a link between two nodes where they're both holding these quantum processors, and there's this quantum connection which is made out of there's actually a midpoint Bell state measurement detector, and then linking it are these two quantum channels. And what sort of actually physically characterizes this network is the models you put on those components. So you determine the delay on the channels and the loss, and in this way you characterize the physical behavior. Does that answer your question?
Perfect. Yeah, exactly. That was it. And I guess just one more quick one then. Once we have these topological elements as a tool, do you also have versions that have been calibrated against, say, real fiber or whatever, or is it still like a high-level model where you tweak the knobs as you wish when you put the simulation together?
I'll give some use case examples of where we've used NetSquid to model physical setup and validate it against experiment. Regarding fiber, we typically use quite simple models for the things we're trying to study, which generally focuses on the more quantum characteristics of devices. So for fiber, for instance, we typically just take a loss model of something like 0.2 dB per kilometer, and maybe some sort of intrinsic loss when the photon's entering that channel. So that it's just an exponential model we would use for something like that. But sort of the memory models in terms of sort of T1 and T2 noise on a device. So how does it dephase? And I mean, again, they're not very complicated models, but put all together, they will characterize these devices. Great. An example of
maybe a quick follow-up on Itish's question. You show that you can model the classic channels. Are they also just modeled as discrete event with the classical model, like you're talking about the fiber optic loss? Do you also model the control operations?
To answer your first question, so the classical channels behave very much like the quantum channels. What's different is in the types of models they accept. We have experimented with classical loss and different types of encodings, and what if you would lose a packet. I think the guys really focusing on the link layer simulation, as I'll come back to, also experimented with that. But generally, we're using the classical channels to sort of convey things like heralding information or corrections. And the only model we typically apply is just a delay. So how long is that information taking, the classical information taking to transit the channel? Like I said, we experimented with things like classical loss, but moved away from that. I mean, it's interesting to test the robustness of a protocol, so it was experimented with.
Okay, thanks.
I say it like this because it's been a while since I've seen or heard anyone talk about sort of classical loss models. But it is something you can add. I mean, the channel itself is very generic and it can accept the loss model. But then, yeah, it's up to you to define what that means. So if you put some classical message on the channel in some form, you're free to encode it. You're free to apply loss to maybe certain bits or to the whole packet. But in that way, it's maybe good to emphasize NetSquid is also, and with this modeling capability, trying to be a framework. So trying to make it easy for users to define these models. So we certainly don't have a model for all these different kind of effects that might be interesting.
Thanks.
Yep. And then zooming in on the sort of the most complicated general component we have, which is the quantum processor. So this is a quantum memory in that it has different positions that can store qubits. But it adds to that the ability to configure also instructions. Think of instructions as gates, but also different physical processes and manipulations of these qubits, together with the topology of where these instructions are possible. So the quantum processor is in that way also a framework for how you can describe different processing devices. And that lets you model these different devices. So there are models at QuTech for NV centers and trapped ions processing devices using this generic component. So for an NV center, for instance, so it has a nitrogen vacancy center. That's its communication qubit. That's what can emit an entangled photon. But around it, there are also these carbon-13 atoms that can be used as storage, that can entangle with. And that topology, that's a star topology. So each carbon-13 can really only interact with that communication qubit, which also makes it quite interesting to use these NV centers from a control perspective, because if the NV center is entangling in one direction, it can't simultaneously be entangling in the other. And when you're done entangling, so this communication qubit is now entangled to the left, and now you also want to entangle one of your qubits in the other direction to another device to the right, you first want to do a swap. So you store that qubit by transferring the qubit into a storage qubit, freeing up the communication qubit to do something else. And it's then possible to specify the different types of instructions possible individually on these qubits, and typically it's not possible to address these storage qubits, but there is an entangling or swapping gate between the communication and the storage qubit. Trapped ions, that's sort of a different story. Here you have these ions being trapped magnetically and electromagnetically in a line, and they're all individually addressable, and they're all equal. Well, you can have different species of ions, but in the simplest case, they're all equal. And it's in principle also possible to pick any two of them and apply an entangling gate. So this is a very different gate set and a different topology. So the idea of the quantum processor is that you can configure it to be able to describe both of these devices or any other device you find interesting. And then on top of this processor, I realize I should speed up a bit. On top of this processor, you can define a program that can run. So you define sort of physical instructions on the processor, and then you can define a more generic program in terms of sort of more abstract instructions. And this is really like a circuit, but a little bit more in that it also supports conditional logic. You can run a mini circuit and then yield, get the result, and then depending on the result, proceed with your calculation. And it also supports, and then, yeah, you can inform the processor whether to run certain instructions in parallel. Then lastly, so that was the modeling of the physical network, the physical components.
So one quick question, Rob.
Yeah.
I mean, IBM has this famous for Qiskit toolkit for some of the things that you mentioned, the high level things. Is it equivalent, or can you hook Qiskit into NetSquid, or how does it?
Yeah, no, we don't have. We don't have an interface to Qiskit. This program here you can see is similar to the kind of program, the kind of quantum circuit you would describe in Qiskit, indeed. So you define here free qubits, so sort of in the sort of musical bar analogy, these free lines, and here you're defining gates on these qubits. The difference is the timing aspect. So these instructions, they get translated to physical instructions and actually take a certain amount of time and may also come with a certain amount of noise. So quantum circuit simulators like Qiskit will generally insert noise by adding gates. We effectively do the same, but we make it time dependent, which is quite crucial for the networking aspect, because that's sort of the random feature that makes it also challenging, is that, I mean, you have a lot of different logic going on between nodes, and at the same time your qubits are always sitting there decohering, waiting for each other. And that's the part we're trying to capture here. But indeed,
that makes a lot of sense. This is taking the physical aspects more into mind than just a simulator.
Yep. Right, and then lastly, on top is this protocols subpackage that describes the classical logic or behavior of your network. So you can define protocols locally on nodes. You can also define a protocol across nodes. But in principle, the more realistic thing is to define sort of the logic you want to run on each node. So here's a very short example of sort of a simple game where two nodes play ping pong with a qubit across a channel. You would transfer that as a protocol by describing the logic as one node waiting for input on a channel. One thing I didn't quite mention earlier was that these components interface with each other using ports, and they can be composed of each other, also with ports. So in this case, the protocol is waiting on this input port for a qubit to arrive. It arrives, it does some form of computation. In this case, it measures it, prints the result, and sends it back again through that port. So this is using these yield expressions. So there's asynchronous I/O flow. It's also possible to program these protocols using callbacks. So that's the different pieces of NetSquid, the different sub packages. Here's very quickly, as I say quickly because I realize I only have 20 minutes left. I still have a number of slides. Here's a sort of an example of how a NetSquid simulation would work. So let's say we were simulating the performance of this quantum repeater I described earlier. So these two end nodes with a repeater node in between. And they're both first trying to establish entanglement, and they want to distill it, and then they want to swap it. So the first step would be modeling the setup using components in NetSquid. You place your nodes, connections with nodes inside the connections. So that's the modeling step. You would then apply the logic, so the protocols to each node describing what they're trying to do. So they're trying to first generate entanglement. Then when they have two copies of it, they distill it. And then for the middle node, for the repeater, if both sides succeed in creating distilled entanglement, they perform a swap. And that could be your termination criteria. So the moment this setup performs one swap, you say, great, it's done. Let's check how long that took and what the fidelity was. What you see in this example, so these are qubits being created. And you see sort of discrete event timeline proceeding is, in this case, the second pair of qubits are created and now distillation takes place. But of course, the fidelity of the first pair, because they've been sitting in memory, has decohered. But distillation succeeds, the circuit is applied, and now these qubits wait. And here below, I mean, it's the same scenario I sketched earlier, but now there's a failure, they start again, success. But yeah, what's critical here is that these qubits, which are sharing states, are continuously decohering. And so one interesting metric here is, what's the final fidelity of this swap? Okay, so you run the simulation once, and you can measure these results. But if you want to analyze the performance of the network, in the simulation, what you really want to do is you want to run it n times. You want to run it 10,000 times and explore the probability phase space, if you will, of what's possible. because in NetSquid, quantum operations can be done purely quantum mechanically, in the sense that if you're using, for instance, density matrices, which are a distribution of quantum states, if you do a specific operation, you might end up in multiple pure states, and NetSquid can track that for you. But whenever there's a measurement that produces a classical outcome, we always roll the dice. We always make a choice and produce one outcome. So we stop tracking that actually quantum mechanically, you know, the cat could be both dead or alive and create two different paths. We choose one. And we do that because that classical output then has to be fed into classical logic that steers the simulation in one direction. So one simulation run sort of follows one path in probability space. And to say something about the performance of the network, you want to do that many times and then statistically analyze the outcome for all the different paths you've explored. So to be able to say something about the average fidelity your repeater can produce, or the rate at which it can produce it. Okay, so that's how NetSquid works, and then some of its internals. So I'll now describe a few use case examples. Any more questions about the last section?
No, I wish there are some canned examples so we can get kind of just look at how you put something together.
I had just one quick question.
Yeah.
Yeah. So regarding the decoherence, is that something? Can you specify the actual process, or some sort of a random process by which it decohers, or is it something fixed?
You're completely free to describe your noise or error models. So these are models. They're sort of like functions you can put on your. So I'm sort of moving the problem to the user right now, right? But we do provide a few base models. So we have depolarizing noise, dephasing noise, T1, T2 noise, amplitude damping, and you can then specify the parameters to those models. So what is the probability, or you can make them time dependent. So the noise model will get, let's say it's a memory noise model or a channel. When it's about to be applied, it gets as inputs the time, if applicable, that, for instance, the qubit was sitting in the memory, and the model can then use that time to calculate the probability with which the noise is applied.
Okay, thank you.
Okay, so use case examples. So I think it was Jitesh. I hope I go into enough detail here, so that please ask questions, because these are maybe a little bit high level demonstrations, but I'm happy to try and give more detail maybe about questions around setup. So the first project NetSquid was applied to was designing and validating a quantum link layer protocol analogous to sort of the classical OZ stack, but then for a quantum network, what would a link layer protocol be? It would, the physical layer, sort of the raw layer, was generating entanglement stochastically, and so therefore not reliably. The link layer would be a layer on top that would offer entanglement on request robustly, and also hardware agnostically. So if you had this link layer protocol, the layers on top wouldn't even need to know that it was nitrogen vacancy centers or trapped ions underneath. They request certain entanglement from it, maybe a minimal fidelity, and they wait for the result. So NetSquid was used here to first, model. It was used to validate and study the robustness of this protocol. And to do that, we modeled the NV center setup in Delft. So 2 nitrogen vacancy centers doing a single click heralding scheme to entangle. And this was compared with experimental data to check that the modeling indeed produced also the measured fidelity and success rate seen in experiment. And once that was confirmed, the robustness of this link layer protocol was studied, and also different performance trade-offs. So under sort of what conditions, does it produce certain fidelity or throughput or latency? And yeah, some students also looked at scheduling. So if you were to schedule different tasks, how effective would that be? So that's one example where NetSquid was used to develop a sort of control plane protocol. Another one, this was the work of the co-author Tim Koopmans for his PhD, was to study the control plane of a quantum switch. So Diane Bardian, I think, and the group of Don Townsley, they proposed this quantum switch that can generate in-partite GHZ states between different leaves in the star topology. And they found that if they model the losses on these links, which have different lengths, using Markov chains, they could come to an analytical solution of the sort of the mean capacity. So for a given in-partite GHZ state, how many are produced at a given moment. And they could solve this analytically. But Tim showed that by using NetSquid, he could, well, reproduce their analytical results, but also sort of push the boundaries into where this became analytically too challenging. So for instance, in the original paper, they couldn't consider a node where the memory available was unbounded. It didn't reach a steady state for the Markov chain, but NetSquid could simulate that. And also going to more than a two-partite GHZ state, which is essentially a Bell state, to four-partite. Analytically, they could establish a bound, but Tim could, with NetSquid, really actually determine the capacity in this case. And Tim also went beyond by adding time-dependent noise to the setup, so that he could not say something only purely about the capacity, but also the fidelity that could be produced. So that's another example of where NetSquid has been used. Another one also that Tim has worked on during his PhD is the parameter sensitivity analysis for repeater chains, focusing on in these nitrogen vacancy centers in diamond. This is, in the end, quite a challenging control setup because of the single communication qubit. So you're having to, yeah, I mean, you can only ever use it to do one thing, and then you have to store its result and look the other way. So Tim, one thing he did was speed up the simulations by inserting states. Sorry, let me speed up. So inserting states rather than taking the link layer approach of really simulating all the physical events within entanglement generation. So he instead sampled those from a distribution. He could model the different protocols he considered, so with distillation or not, whether to swap as soon as possible, using sort of sub-protocol blocks that did specific tasks and reusing those. So that in a protocol way was quite modular. And in the end, what he analyzed was sort of the sensitivity study of sort of improved future parameters. So he gave a definition of what it means for a specific parameter to be 10 times better than it is now. And he compared that to near-term parameters for a specific chain. Yeah, he in this case observed, for instance, what parameters were the most sensitive in terms of improvements, such as detection probability. In this case, a combination of 2-qubit gate noise, just purely as an example. And at what distance regimes it actually becomes interesting in these near-term and future scenarios to have repeaters. Because at shorter distances, you see in this plot here, it's actually more performant in terms of fidelity and rate in some cases to not have the repeater set up. And then I think this is the last use case example. So at QuTech, we've been involved in the Quantum Internet Alliance, a European project to develop a blueprint for pan-European quantum internet. Different parties, different labs with different devices for processing qubits. And here, 2 master students within QuTech, or former master students, used NetSquid to do a performance comparison of different atomic ensemble memories. So different types, 2 different types in a repeater setup to see when one is more performant than the other. In this case, one was good at multiplexing, one is a higher efficiency. And this had already, by Saikit Guha and co, been modeled in quite some detail, but their simulation added extra physical details like multi-photon emission and time-dependent memory efficiency and so forth. Yeah, so it's a range of examples of where NetSquid's been used. Just a few more that I'll go into less detail. But for instance, by I forget his name. Maybe it'll come to me. A group in MIT, Dirk England, used NetSquid to sort of design and validate a quantum router architecture, QuTech, quantum network data layer protocol, and so forth. So that's a list of examples. Maybe I'll quickly go through the final slides, and then if you still have that question, Yotesh, about the use cases, feel free to ask. It's got a proprietary license at the moment, but it's free for academic use. It's so that requires you to register on the forum and use those registration details to download it from its package index server. And then a good place to start is the documentation. So we have a NetSquid in 10-minute guide, but also a bunch of different tutorials and description of the API. NetSquid, like I've said, should be seen as a framework. So we provide some generic models and especially these general components. But our hope is actually that users provide the actual detailed modeling. So online we provide open source so-called snippets or extensions from QuTech, where the physical layer and generic framework for a physical layer has been realized, and then nitrogen vacancy modeling, trapped ion. Actually, I think trapped ion is not yet available, but atomic ensemble modeling, different extensions for adding memory managers and other types of classical logic. When we started NetSquid, this field was still quite small, but now there's a number of simulators out there. Probably the most similar two are Sequence and QWISP from Rodney Van Meter's group in Japan, and Sequence from Martin Sukura at Argonne in Chicago, and that they also use discrete-event simulation. So they also try and accurately track time, which makes them be able to capture these physical non-idealities. QWISP is a bit different to NetSquid in that it doesn't properly try to track quantum information. It actually does it in a non-universal way, but quite efficient, which really lets it simulate huge networks by tracking the probability state vectors. But yeah, so this is not universal, so it's different to how NetSquid approaches this with stabilizer states. Sequence doesn't, as far as I know, yet have a solution to representing large entangled states. Yeah, the modular modeling framework, that's quite a subjective one. Maybe, yeah, also good to point out some of NetSquid's weaknesses. So it doesn't have a graphical interface. That is something we would like to add, but something we haven't started working on. And it's not open source. This is feedback we get a lot, and also something, yeah, we keep asking. Oh, I'll say something about that on the next slide. Okay, then final slide, the outlook for NetSquid. So interesting to note that on November 19th, QuTech is launching what it's calling the Quantum Network Explorer. So this is analogous to the quantum IBM, sorry, the IBM Quantum Experience. So it's a web front end representing the experimental metropolitan network being developed in the Netherlands between 4 cities. That's still sort of that physical network is, the idea is that users will be able to play with it as they can with, for instance, the IBM hardware backend. But in the beginning, that's still sort of coming online. And so NetSquid is playing an emulator role there, sort of emulating the hardware that will become available. So that will come online on November 19th. So I'm also looking forward to playing with that. We're continuing, so we released NetSquid version 1 last year. So we're continuing with the version 2, where sort of one of the core things we want to add is to make it easier for users to use different quantum information carriers beyond qubits. So for instance, Fox states, qTerts, continuous variable. We won't aim to provide libraries necessarily for all these things in the beginning, but we want to make it easier for motivated users to also be able to insert these quantum states themselves with their own modeling. And yes, we also working on several engine improvements. And then finally, we're sort of actively working to sort of grow the adoption of NetSquid. We hope it will also be used for modular quantum computing simulation in the future. We've been running a tech transfer study the past half year to see if there's also some industry interest in a tool like NetSquid, and at the same time asking if the current proprietary license we have is the best one, and sort of considering also QuTech's business logic. QuTech not being a business, but still sort of a research institute with different interests. Okay, that was it. Thank you.
Rob, thank you very much. We're at time, but I think there's time for maybe 1 or 2 quick questions.
Sure.
Good, John.
So a quick follow-up on the scale of the simulation. You mentioned NetSquid is able to do large-scale simulation. Do you have a description of how large you can go?
That very much depends on what you're doing, because generally the bottleneck is the quantum states. If they get very large, then you should be using, for instance, a stabilizer formalism, or hoping that you can contain the entanglement in your network. I think I have a backup slide here where here, for instance, we did a profile for a repeater chain with 1,000 nodes, which you see scales just linearly here. But that's because the repeater chain, at no point are there 1,000 qubits entangled. There's entanglements being generated and swapped, but we manage this quantum state, as I mentioned, in a sufficient way where, as the measurements are done, the state shrinks again. And in this way, the quantum state, I believe, never gets beyond something like 4 qubits. And so, yeah, for this kind of application, you see it just scales linearly to any number of nodes. But yeah, if the quantum computation you're doing is either involving larger entangled states or needs some non-Clifford gates, then yeah, you're gonna see in this plot, if you're using density matrix formalism, because let's say that's what your noise models need. Let's say you need to do amplitude damping, or you can do that with Kitts vectors as well, but it's the same story. Yeah, your runtime is going to go exponentially with the number of qubits if you've got large states. So that's the bottleneck.
Thank you very much. I think we're at time. Other questions? Maybe.
This might be too complicated, and if so, we can just take it offline. But I've lost track of how time advances in the simulator. So if I do the analogy with SPICE, for example, you move forward through integration against the circuit matrix. In this simulator, what causes you to move forward in time?
There are events on the timeline. And those events are generally classical logic. So, sorry, that's maybe not the best way to describe that, but those events are really sort of classical events. So a qubit's arriving, or some sort of instruction or operation is scheduled from the classical logic. And the simulation engine jumps really between these events.
Okay.
And what's important then is that the quantum information stays accurate and it attempts to do that by looking back and seeing how much time has passed, and then retroactively evolving the state to the current time.
Yeah. Great. Yeah, thanks.
Rob, thank you very much. Really appreciate this, and really appreciate the chance to learn more about NetSquid. And I think there'll definitely be follow-on.